Hello, my name is Robert Smith, and I'm with New River Community College. And today we're looking at solubility equilibria. There'll be two videos involving directly with solubility equilibria. One where you're going from uh, the solubility of a salt to its solubility product, which is otherwise known as KSP, and then the other one will be going from KSP, our solubility product, back to solubility. Okay, and so let's get started. So we're asked to calculate the solubility product of silver chloride, and we're given that the solubility of silver chloride is 1.8 times 10 to the minus 3 grams per liter. This is kind of pretty standard. Um, I didn't put it in milligrams per liter because oftentimes when you're dealing with solubility, it will be in grams per liter. That's just the standard. Sometimes you'll hear about molar solubility, and that simply means instead of grams, they'll be using moles. And that's a little easier to work with sometimes, but in this case, we're just starting off with solubility. So this is just a little bit of terminology. So you have solubility, which is usually in units of grams per liter. You have molar solubility, which will have moles per liter, and then which is similar to molarity, so it's a little more familiar. And then you have solubility product, which is a unitless. Uh, it's a unitless value, and it's denoted as KSP. So it's like our KA, KB. It's just like all the K values that we've had before, except in this case, it's KSP. So for this one, what we'll want to do is, or for each of these cases, whenever you're dealing with solubility, you want to figure out what your reaction that's occurring is. And what it is we have a salt, AgCl. It's a solid, and then we're going to put it in solution. And as we put it in solution, the salt will either dissolve or remain as it is. So we have Ag plus Cl minus. Those are both aqueous. Um, so it'll be in equilibria, which means that's how you get saturated solutions, supersaturated solutions, and so forth that you'll be exploring in your labs. But in this case, what we want to recognize is that if we do a charge balance equation, which means that if we take these species and we think about them in terms of charges, we want our positive charges to equal our negative charges. So that means that the concentration of silver plus has to equal the concentration of chloride minus in order for us to have a neutral species of AgCl. And you can also consider this in terms of, you could set up an ice table, supposedly, but consider that in an ice table, regardless of the scenario, you're never gonna consider the solids. So you would only consider your ions. So if we say plus S and plus S, then these are both considered S. So when we're doing our calculation of our KSP, our solubility product, and we do products over reactants we don't even consider because it's a solid. And recall that whenever we're doing these calculations, we're only considering aqueous and gaseous species. So in this case, we're just going to consider Ag plus Cl minus times Cl minus rather. And because they're both S, that means KSP is S squared. Now, we have this value for our solubility. So that means that each of those values, each of Ag and Cl, because they're equal from this equation here, this equivalency. So we can do our calculation to find KSP, but KSP is in terms of moles per liter when we're doing that calculation. So, we'll want to use the mole per liter equivalent of our solubility. So we first need to calculate that. So 1.8 times 10 to the minus 3 grams per liter times the molar mass of silver chloride. So for every 1 mole, we have 143.32 grams, which would give us 1.3 times 10 to the minus 5 moles per liter. And that's our molar solubility. So now we can say that Ag plus, which is equal to Cl minus, which is equal to S, each of those is equal to S, is also equal to 1.3 times 10 to the minus 5 moles per liter. So when we calculate KSP, the solubility product, we're considering S squared, and we're considering it unitless because it's always in relation to 1 mole per liter. So it's like saying 1.3 times 10 to the minus 5 moles per liter per 1 mole per liter. So S squared, which is 1.3 times 10 to the minus 5, gives us 1.6 times 10 to the minus 10. And that's our solubility product. And that matches the value in your textbook. So we did it right. Thank you so much.